I think we can get started. First of all, I'd like to welcome you to this really incredible scientific session. I think I'm going to enjoy this as much as you are. We have two fantastic speakers today speaking about MRD Solutions for the Studies of Hematologic Malignancies. So the agenda today is we have two really good speakers. So I'm just going to get a very quick overview of the company. We've been around for 21 years. We started as an AMP member. So this is our birthplace, was AMP. We currently supply GMP reagents, ISO 13485 compliant GMP reagents to over 650 laboratories in over 65 countries. And we provide international access to harmonized tests and software, bioinformatics software, for laboratories around the world. We also have our own clinical labs located around the world as well. So, and we partner with pharmaceutical companies to support clinical trials, and we develop and commercialize IVDs and companion diagnostics. So I'll get off the stage here and get to our first of our two fantastic speakers, Maria Arcila, from Deputy Chief Molecular Studies and Molecular Director of Molecular Hematopathology at Memorial Sloan Kettering.
Thank you so much. So the goal for today is to go over some of these assays and to give you an idea of the amazing amount of work that takes into taking these RUO assays and doing a clinical validation to be able to use these assays in the clinical setting. As you know, clonality testing is an essential component of the assessment of lymphoproliferative disorders, and historically this has been done for many years using the most common method, multiplex PCR with capillary electrophoresis, which gives you an idea of the arrangement or the overall spectrum of rearrangements by the size of the fragment, but doesn't really give you information on the actual sequence of the clone. These assays are very robust, and here are some representative plots of what we usually look for when we're signing out these clinical assays. The picture that you see on top right here is what we would look for a polyclonal sample, and what we look for is fragments with a distribution that is bell-shaped, and telling you that there is no single fragment that is prominent, and you can, for the most part, say that a sample that has this kind of distribution is likely benign and just polyclonal. When you're looking for something that is rearranged, you're looking for either a single peak or two peaks like you see here, so you're relying on finding that you have this very prominent peak, and perhaps maybe with that little bit of a polyclonal background to be able to say that something is clonal. However, for those of you who sign this out in a clinical in the clinical setting and see them every day, the vast majority of the samples don't necessarily look like this, but they actually look like this, where you may have a few prominent peaks and you have a very high polyclonal background. These are just extremely challenging because you're trying to call clonality on something like this, and you end up just giving an equivocal because you just don't know if these clones or these peaks that you see that are prominent here are actually a clone or is just part of just prominent but not necessarily disease. So I like these assays. We have been using them for many years, but they have pros and they have cons. So the pros, it's a very simple process, is robust, is very rapid in terms of the analysis, and they also require, these fragment analysis assays require very low DNA input. However, because you're doing you're multiplexing so many PCR reactions, you end up doing this in several tubes, and you do, even though each individual assay requires low DNA input, the overall requirements for a full assay, including IGH and TCR gamma and TCR beta, is actually pretty high. The assays are relatively inexpensive, but then again, it has its cons. And for me, the fact that it separates the products by the length of the rearrangement, but not the unique sequence that you have, is very difficult to use that in the monitoring of patients. The calls, as you could see from the graph that I showed you before, they could be very subjective to interpretation. So one day you may take that one picture and say, well, this is clonal, but then the day after you may just think about it again and say, well, maybe it's not clonal. So very, very subjective in terms of interpretation. And they also have very low sensitivity. So because of that low sensitivity, they are unsuitable for low-level disease assessment or minimal residual disease assessment. So in our lab, we have transitioned to the clonality assessment by NGS methods, and we find that this has marked advantages over the amplicon-based assays that I just showed you, because it allows the identification of the full range of the clonal populations that you see in a sample. You can determine the specific DNA sequence of the clonal rearrangements. You can also, for the B-cell processes, at the same time that you're doing the clonality assessment, you can also examine somatic hypermutation as a prognostic marker for CLL or hairy cell leukemia or even plasma cell neoplasms. You can also detect clonal events that are hidden in a polyclonal background, which with the fragment analysis assays you wouldn't be able to know because they have the same size as the other fragments, but you cannot see the actual sequence. And then of course you can track residual disease very easily because you actually have the sequence of the clone that you're looking for. Beyond the clonal detection, these assays provide you a very, very high resolution picture of the spectrum of immunity that is found in lymphoid malignancies. You may identify in a sample the stable and dynamic aspects of the immune repertoire that would differ under normal conditions or disease conditions. And you can also define the behaviors of clonal tumor populations, and you can see the suppression or reemergence of populations throughout treatment. And this is something that we now do regularly. As you heard already, we use this LymphoTrack assays, and the LymphoTrack assays are just a single-step PCR-based assay for rearrangement assessment in IGH and a T-cell receptor. These assays are optimized optimized multiplex PCR master mixes, and it also comes with a comprehensive bioinformatics package that you can use that will give you the DNA sequence, the clonal prevalence, and also the VJ family identity for each of the rearrangements. So this is the IGH assay, and as you can see, it has several sets of primers that capture the FR1, FR2, and FR3 regions, the same as the fragment analysis assay. But also for the somatic hypermutation package, it has these lead primers that lets you capture additional rearrangements that you may not be able to if you have somatic hypermutation in the FR1, FR2, or FR3 regions. The T-cell receptor gamma gene rearrangement is very similar to the version 2.0 in the fragment analysis. So what I actually want to do now is just go through our experience in terms of validation and the workflows of these assays. So we have validated the assay for the initial assessment of the clones and also for tracking of these clones at low level. And we have been working for the past year in validating the minimal residual disease aspects, which is what you're going to hear today. So in terms of establishing a diagnostic clone, this is the software output that you see from Invivoscribe. And what it does is, well, it gives you all of the clonal sequences that you have in that specific sample. And here I'm only showing you 12, but you get the clonal sequence on the left side, which is here, and you don't see the entire clonal sequence, but this you can expand. It gives you the length of the fragment, and it also gives you the raw count for those fragments, as well as the VJ rearrangement. It also gives you information on the total number of reads that are supporting that clone, and it gives you the mutation rate, so for the somatic hypermutation assessment. This is how a sample that is clonal would look like. So it's a single clone that is identified, all of which has the same sequence, and that appears in here as a solid bar that is green. For comparison, for those of you that do the fragment analysis assays, this is how it would look like. In here, the fragment is organized by the size of the fragment, and in here is by the VJ rearrangement that it has. And here is the sequence, for example, for this specific sample, where 60% of the total reads have this specific sequence that is here, which we will later use for for subsequent samples to be able to track disease. When you're looking at a polyclonal sample, it looks more like this. So all the specific sequences, but nothing that is actually restricted to a specific rearrangement. So in this case, what you see is multiple bars in here with different colors. So this is the distribution that you would see in a sample that would look like this. This is a TCR gamma. So this is the equivalent to that in the two different assays. So there are specific interpretation rules for a primary diagnosis, and so what we actually have set up is that we require to have at least 20,000 reads overall, but in general, for all of the samples that we have more than 500,000 reads, so the sensitivity with that number of reads would be very high. We require for the clone to be at least 2.5% of the rest of the reads, and also 3 times the background reads. And that's what we usually use for the initial assessment of the patient. In terms of the sensitivity, I wanted to actually show you the difference between the fragment analysis assay and the NGS assay. So one of the things that is important about this assay is the fact that, for example, in here at 5%, this is a 5% dilution for the sensitivity study. In the fragment analysis assay, you can see that there is a clone, but you start seeing the polyclonal background. Once you dilute the cell line, for example, to 1%, you can no longer see where the fragment is. So this is something that you would call negative by the fragment analysis assay. However, with the NGS assay, you can safely call that a clone without a problem. If you went down to lower levels, you could still call this a clone. So even though we used the 2.5% as our cutoff for the initial assessment, for many cases, if we know that this fragment may not necessarily be 2.5%, but it's at least 10 times the background, then you know that you have a clone. It's just that it's at low frequency. So the sensitivity of the assay is far better than the fragment analysis in all of the samples. With the TCR gamma, the results are actually more striking. As you can see with the fragment analysis assay for the gamma, even at 10%, you have a very hard time calling this a clone. You would say that there's a prominent peaking here, but not necessarily clonal, and then you completely lose it as you keep going. With the NGS assay, you can clearly see the clone at 10%, at 5%, and even at 2.5% and beyond that, similar to the IGH. So that was for the diagnostic. So how do we move into MRD testing, and how does it actually work with our clinical samples? So the first thing that we had to do for the validation of the assay was to establish the required input, assessing the limits of detection, and also the rules and the workflows for the detection of MRD. So one of the things that is important when you're doing these MRD assays is that, well, you have to make sure that you don't have perhaps a minor contamination from from the diagnostic sample where you have the clonal sequence at a very, very high level. So we always make sure that we do not run the diagnostic sample with the MRD sample. So for example, a patient, they require an MRD assay, and we don't have the diagnostic sequence yet. What we would do is run the diagnostic sample first, and then in another run the other one. So that's part of the workflows, and they can be pretty extensive. So in terms of establishing the required input, DNA input is obviously critical. And the more DNA template that you have, the more the sensitivity is going to be for your assay. So if we looked at the theoretical yield for a single cell, that would be 6.5 picograms of DNA per cell. So if you wanted to get, with any assay, to a sensitivity of 1 in a million, really you need a input of at least 6 to 7 micrograms of DNA. And there's no question about it. So through the validation that we did, we actually confirmed that this is the case. You definitely need that much template to be able to get to that sensitivity. So for a clinical assay, well, you have to decide how much can you actually get, well, can you actually do this clinically? Can you get to that sensitivity we had without having to run multiple tubes and then have an entire run that is only that one patient to be able to get to that sensitivity? That's not something that we could possibly do with the assay for us. So what we're doing is we decided on a cutoff for our validation, and our cutoff was between 1 times 10 to the minus 4 to 1 times 10 to the minus 5, with an input of about 1 to 2 micrograms. We can actually get to this sensitivity. And so the next thing that we wanted to see was, well, how does this actually relate to flow cytometry, for example? Is this equal, or do we need to go for a higher sensitivity? So what this table was provided by Invivoscribe of some of the of what they recommend is the input. And so in here you see that if you want an input of 1 times 10 to the minus 4, you actually do need to run at least 2 replicates of 2 replicates of 0.5 micrograms. And then that way you can run the maximum number of samples. If you want to go beyond that 1 times 10 to the minus 4, then you need at least 3 to 4 reps, which means 4 different tubes or 4 different reactions. But then you cannot run as many samples per run. So this is one of our dilution studies, just to show you how many reads and how much can we actually do with 2 micrograms input. And here what you see is actually a dilution study for a cell line, which was our Invivoscribe 000 divided, that was diluted with, actually it was a 0013 that was diluted with Invivoscribe 000 control. At the diagnostic level, that sample was about 72%, it had a 72% clonality, so the dominant clone was at 72%. So when you take that and you start with your dilution from 1% all the way down to 0.0001%, which is 1 in a million, with 2 micrograms, you actually cannot get to that point. So you require, when you're doing your studies, or we require that we have at least 5 reads of the diagnostic clone in that sample to be able to call it, we have detected that clone. So here, with a 2 microgram input, we can actually see that at 1 in 100,000, so 1 times 10 to the minus 5. So in between 1 times 10 to the minus 4 and 1 times 10 to the minus 5, you can actually get to that sensitivity with 4 micrograms. You can see that the dilutions, when you run these samples, the linearity is actually very, very good. Also, the inter-assay and intra-assay reproducibility is equally good as well. So how does this actually translate with real clinical samples? So in the validation, you usually work with samples that have ample material. But then when you run into the clinical samples, well, you may not have that perfect material that you wish you had all the time. So this is a table from some of the samples that we did on our validation. This is actually 48 patients with 62 samples altogether for the follow-up of those 48 patients. And we had several disease processes, as you can see here. We had 11 acute lymphoblastic leukemia patients, 16 mature B-cell neoplasms, 9 mature T-cell neoplasms, and 12 plasma cell. So how does this perform when you actually do these samples? So the first thing that we wanted to do was, well, what's our comparison to the standard capillary electrophoresis assay? So we had 57 patients from that set, or 57 samples from that set, where we had both the CE and the NGS testing. And these are the results. So it is clear from what I have already showed you that the sensitivity of the LymphoTrack assay or the NGS assay is much better than CE. So this shows you exactly what we expected. So in this case, what you can see here in the red bar for each individual one of these disease subsets is that the LymphoTrack and the CE can pick up a clone in most of the cases. However, what you do see here in the green graph and in the green bar is that the disease that is detected by the LymphoTrack assay only is much higher. So the assay is definitely much better than the CE to be able to detect residual disease. But we already knew that. So what about something that we already have for minimal residual disease assessment, and that is flow cytometry. So in here we have 56 samples. where we're comparing the results of the flow cytometry and the LymphoTrack assay. And what you can see here is that in many cases, well, you have the blue here is no disease detected by the LymphoTrack or the flow cytometry, and that's many of the cases. The red bar is when disease is detected by both the LymphoTrack and the flow cytometry. And that's also quite a few cases, but in every single one of the diseases here, except for the plasma cell neoplasms that you see here, the LymphoTrack assay proved better in detecting minimal residual disease, detecting at least 20 to 30% more cases with minimal residual disease compared to the flow cytometry assays. The only disease process where this was not the case was here, the plasma cell neoplasms, where the LymphoTrack did not pick up some of those cases, but it was actually the flow cytometry that detected disease and not the NGS assay. And we will go back to these specific samples because they actually turned out on the follow-up of the patient that these were false positive by flow cytometry. So here is one example of one of these patients that we're following. We have a 26-year-old patient with TALL, and here is the diagnostic sample with 2 clones that we're tracking through subsequent studies. You can see here that the 2 clones is actually it's a single clone with 2 rearrangements, perhaps, which are at 34 and 28%. In this subsequent sample, which was 1 month after the second allogeneic transplant, at this time the patient has no disease by flow cytometry, and there is no disease by morphologic assessment. However, with the LymphoTrack assay, we do pick up the disease at very low level. As you can see here is 0.01, almost 0.02%. Clearly, with the fragment analysis assay, you just cannot pick up anything like that. It so happened that this patient did in fact have residual disease, even though it was not picked up by morphology or by flow cytometry. About a month later, the patient had the diagnostic clone picked up at 0.019% by flow cytometry, and the PET scan showed that the patient had relapse. So this is one where we could clearly prove that the NGS assay was much better than the other ways of tracking this patient. Again, the same patient at 6 months and 8 months. At 6 months had positive flow cytometry and also had 1% blasts later on, and we can pick up the clone again. And then at 8 months, flow cytometry again negative. Patient is in morphologic remission, but the LymphoTrack assay continues to pick up the clone. In this case, now both of the clones are picked up and at much higher frequency. In terms of the MRD assessment of plasma cell neoplasms, so as you know, plasma cell neoplasms are difficult to assess even by flow cytometry, and that is because you usually have a bone marrow that is loaded with disease, like this patient, 65-year-old male, who had multiple myeloma. The bone marrow biopsy shows 40% involvement, but when you actually do the aspirate, you end up with very, very, very few plasma cells. So assessing those samples is just very difficult. In terms of the flow cytometry, this patient, for example, had 10% involvement, and in the diagnostic sample, and then with the NGS assay, we found the clone, as you can see here. This is the sequence of the clone, and it was present at about 5%. So in the post-treatment sample, when you already start at just 10% clonal sequence, you know that later on the assessment of that patient is going to be very difficult. So this is now the post-treatment sample in that patient I just showed you. Morphologically, we just really couldn't tell that the patient had disease because had scattered plasma cells that with the immunohistochemical stains, we really couldn't say that this patient had any type of clonality. By flow cytometry, we picked up about 0.3% of the total cells were plasma cells that were abnormal, and in this case, both the flow cytometry and the NGS assay picked up the sequence. So this is a patient that has minimal residual disease with evidence from 2 different studies. So I did show you this slide before. So for the plasma cell neoplasms, this was the only case where you had cases that were picked up by flow cytometry, but they were not picked up by by the NGS assay. So this purple bar that you see here is actually 2 patients. So these 2 patients were interesting because when we followed up these patients, so one of them, even though the patient had disease by flow cytometry in about 2 or 3 different times, by the LymphoTrack assay, we just really couldn't pick up anything. So in the 2 subsequent samples from the same patient, we had absolutely no evidence of disease. The patient was all donor. This was a transplanted patient. So this was a false positive by flow cytometry. So the patient is now being followed with only the NGS assay. And so patient number 2, there was an abnormal plasma cell population by flow. And unfortunately for this specific patient, we just didn't have enough to be able to do 2 different runs, which would give us the maximum sensitivity. But in one run, we did have 1 read of the clone supporting that the patient had residual disease, but we really couldn't call this a positive because we require at least 5 reads to be able to call minimal residual disease. So what happens with all of these other patients that we have here that have been negative positive by negative by flow, but positive by NGS? So we're following these patients, and so far 2 out of the 10 patients with plasma cell neoplasms here already had recurrent disease at follow-up. So it does seem, while we have to collect more information and probably, at least a year on these patients, we can say that the NGS assay is providing more information than the flow. Now, another patient subset where we really find this assay very helpful is in the monitoring of patients with B-ALL. And this is for 2 different reasons. So this is an example of one of the patients that we're following. At the top in here is the first time that we tested the patient, and you can see that the patient has 2 clones. One that is the prominent, the other one is just a very small clone. You see exactly the same 2 clones by the NGS assay. This is now the subsequent sample for this patient. And as you can see, now we have 1 clone that is different to the other one. We confirmed that this is, in fact, a completely different clone. So incidentally, we couldn't figure out what was happening with this patient at all. It was like, well, this patient has a clone, either a clone that is completely different disease, or or we have a contamination in the lab. So we went looking for a contaminant because we couldn't figure out what this clone was doing on this patient. But we went back to several patients that happened to have this clone, and this just happened to be the CAR T cell construct, the CAR T19 that these patients were being treated with. So these patients with B-ALL, not only can we monitor the disease, but we also can monitor the CAR T cells and how they start going down or up after they are treated with them. So it's a very helpful assay to do both things. For this patient on the subsequent sample now has no CAR T cells and has the same clone that they had before, but in addition to that clone, they have an additional clone, which you can see here. So we're trying to see exactly for these patients that are getting some type of immunomodulation or immunotherapy, what happens, what are those additional clones that we're seeing, but these clones do happen to survive after they're being treated, so we have to follow up a little bit more. So what you can see here, this is that last example. You can pick up the clones that we were intending to look for, but then in here is the CAR T cells that are now at very, very low frequency, about 0.05%, but they're still there. So in terms of the diagnosis and monitoring of T-cell neoplasms, we find that the NGS assays have the best use in the T-cell neoplasms. So, usually when you have a B-cell neoplasm, you can easily track that kind of a population with flow cytometry. But with the T-cell lymphomas, it's actually difficult to do this by flow because sometimes they just don't have the abnormal immunophenotype. But in this case, you're actually looking for the specific clone on this patient with the NGS assay. So just to drive your attention back to this in here, this is actually the one case where we pick up the most clones with the NGS assay compared to CE, but also the most clones compared to flow cytometry, and is almost half of the cases where we actually can do that. This is one of those cases where we found this assay very, very helpful. This is a 50-year-old male with a growing subcutaneous nodule in the arm that was an angioimmunoblastic T-cell lymphoma. This patient also had Waldenstrom's macroglobulinemia, so it had an infiltrate of plasma cell of the plasma cells that were neoplastic around the angioimmunoblastic T-cell lymphoma. So with an NGS assay like this one, you can actually track both of them at the same time with the same assay. In this case, the T-cell clone is what we're actually tracking. So these are two different clones that you see down here at 14% and 7%. So the diagnostic clone here at the top with the corresponding NGS results in here. When the patient has a bone marrow biopsy that had no evidence of disease by morphology or by flow, even the fragment analysis assay gives you a hint that there is disease in that bone marrow, but you cannot really call it because it's just too low and there is too much of a polyclonal background. With the NGS assay, you can easily pick up the two clones, as you can see here. Post-chemo, this patient, now pre-transplant, well, what do you do with this patient? Do you transplant this patient or not? Does this patient have any type of residual disease? And clearly, with the current assays by fragment analysis and flow, you cannot do it. But with the NGS assay, we know that that clone is actually there when you look for the specific sequence. This is the review of that patient. We actually ran this patient 5 different times, so we have a sensitivity that is at least 1 times 10 to the minus 5, and in every single one of the runs, we pick up the sequence at about 1% or 0.9. So this patient had disease, residual disease, pre-transplant. Other cases that are particularly difficult are patients that have more than one T-cell lymphoma, and this is one of those patients. So this patient, for example, is a patient that came in with a parotid lesion that was diagnosed as peripheral T-cell lymphoma, not otherwise specified. In this case, this patient has 2 independent clones that have the same size, so both of them are 111 base pairs. That makes it look by the fragment analysis assay as having a single clone, but it's actually 2. You can see here in the diagnostic sample the 2 clones that we're following. This patient had, at the time that the patient was diagnosed, had a bone marrow biopsy and also blood tested. So with the actual morphologic diagnosis and in the bone marrow was that the patient had a T-cell lymphoma. So it was assumed that the patient had exactly the same T-cell lymphoma that was in the parotid lesion, was also in the bone marrow, but with the NGS assay, we knew that this was actually not the case. So you can see here, this is the parotid lesion, this is the blood and the bone marrow in that 2008 sample, and this is actually a completely different clone. In here, because there was a polyclonal background and these 2 peaks were different to that one. In here, we just said, well, maybe this is just a pseudoclone. This is not a different lymphoma. But when you run the NGS assay, you know that it is a different clone with a completely different sequence. This patient was followed up all the way to 2013. The parotid lymphoma, he was cured from the parotid lymphoma, but the bone marrow continued to show exactly the same clone and had active T-cell lymphoma in circulation, but it was a completely different lymphoma. So very interesting patients that you wouldn't know that they're out there if you're not doing the NGS assay. So in conclusion, I find this assay it can very efficiently detect the IGH and T-cell receptor rearrangements, and you can do both of them at the same time, so it's only one testing that you have to do for each individual patient. Clearly, compared to the CE and the flow cytometry, I think that NGS provides, if not comparable, the same results. It actually provides better disease assessment in terms of MRD. Similar sensitivity, but actually better specificity because you're looking for the specific clone for that patient. So in terms of the limit of detection, is completely dependent on the input. So the more runs you do, the better you will be able to assess that patient all the way down to 1 × 10⁻⁶ if you want to. But in our experience, even with just 1 microgram of input, that brings us to a sensitivity of 1 in 10,000. That already provides similar sensitivity to the flow cytometry assay because you're looking for this specific sequence.